Well, good morning. This is Math 1, 237, Linear Algebra. We're going to get started on the slides, but I have a couple of announcements to make. Because the second mini term has begun. Okay. Actually, second mini term began last Friday. That was midpoint of the term, sometime between Thursday night and Friday morning. So we're now in the second half of the term. And the reason I'm saying this, my office hours have changed now because I picked up a second mini term class that meets Tuesday, Thursday, 3:15 to 5:45 for the class, and 5:45 to 7:45 for the lab. So that means my Tuesday, Thursday office hours have been shortened. They now are 12:15 at the end of this class until 3:15, the beginning of my second mini-term class. But not only does it affect my Tuesday, Thursday class, it also affects my Monday, Wednesday. Technically now my office hours on Monday, Wednesday are only my lunch hour, which is 11:15 to 12:15. Because technically I'm supposed to leave at 2 o'clock and my Cal 3 class gets out at 1:55. However, I'm not going to leave at 2 o'clock every day. In fact, seldom, if ever, will I leave at 2 o'clock. I'll probably hang around at least until 4:45 most days, maybe even 5:15, unless there's some reason I have to be later. So, but technically my office hours disappeared on Monday, Wednesday, except for my lunch hour. So that's the only major announcement I have to do. Any questions before we get started? All right, we're in Chapter 4, Section 4.1, top of page 147, vector operations. Is this right? Seems like we did this, but maybe not. What do you have? Yeah, okay, good, okay. That's where my mark was. I just couldn't believe that we didn't get any further last time. But anyway, so our one basic vector operation is vector addition. And to add two vectors in the plane, you add the corresponding components, okay? So if you're talking about the sum of u plus v, let me get my pen activated. U plus v. Now, okay, that just sort of flicked on and off. I don't know why. Did you see it? Huh? It does, okay. Anyway, in 2 dimensions, this would be, and we talked about this before, your textbook expressive vectors in parentheses, the same author in his trig book put them in angle brackets. I like the angle brackets better, so typically I go back and do this. In the book, though, these are parentheses. Either one works. U1, U2, those are the components in 2 space for vector A, vector U, plus vector V would be V1, comma, V2. Okay, and the sum of those 2 vectors would then be a vector, and that's supposed to be an angle bracket. I hit the thing, it doesn't look very pretty. U1 plus V1, comma, U2 plus V2. You just add the components component by component. If this, say again? This is like the 3rd time I've learned to add vectors. Exactly. Now, the other thing is this would work for no matter what dimension vector you read. If this was a 15 space, okay, that'd be U1, U2, U3, U3 up to U15, and V1, V2, V2, V3 up to V15. You add U1 plus V1, comma, U2 plus V2, comma, U3 plus V3, yeah, all the way up to U2, U15 plus V15. You know, whichever space you're in, you add components. Now, let's go back to 2 space because, yeah, geometrically, I can't do this in anything beyond 2 and really make any sense. And that would be this. And let's just arbitrarily choose, because the book did, to put both of these in the first quadrant. Say that was vector u, okay? And this was vector v, okay? Well, u plus v would have been either start with u and then take v, transport it up till its tail is on the head of u, and then it goes up in exactly the same direction at exactly the same magnitude, and then this would be the sum of u plus v, which of course is a vector. But that also is the same as starting with v and adding u to it. Same magnitude, same direction. That's still u, this is still v, okay? And you get the same result. Now, this is probably a little beyond what they're doing now, but this is the illustration that addition of vectors is commutative. It doesn't matter which order you do these. Now, this works in free space, in space, any space. I just can't draw very pleasantly in anything beyond 2 space. You can do some rendition maybe in 3, but beyond that, hang it up, Jack. Okay. But you see, this also illustrates what we did here. This would be U1. This would be U2. This would be V1, same as this V1 down here, if that were level. This would be V2, and sure enough, U1, U plus V would be U1 plus V1, that gets you to here, and then U2 up here plus V2 here, that goes straight across to there, that gets you to there, and sure enough, those are the components of your vectors. So they don't, yeah, they show that somewhatly on the slide here. Okay. This would be you could look at this as V1 down here plus U1 here. And this, what's that?
It's basically like U and V are the hypotenuse of triangles.
Right, exactly. Right. This would be V2, and this would be U2. Okay. Either way, whatever side you want to put them on, you see they do add that way. All right. The next example, one of the vectors you will add is the 0 vector, 0, 0, and it's denoted by bold 0, which is a vector as opposed to a scalar, but you really do need to designate what space. These are 2 space, so no sweat there. So let's clear this so we can do example 2. 2a. U, vector U is 1, 4, again in 2 space. Vector V is 2, negative 2. And what does it ask for? Find the sum of those 2 vectors. U plus V without too much effort would be what? 3, 2. Got it. B would be U equal 3, negative 1, not negative 2. V equal negative 3, 2. u plus v
0, 0.
would be the 0 vector, 0, 0, and we denote that as 0 with a vector sign. Okay. And C, u equal 2, 1, v equal 0, 0, u plus v would equal 2, 1, which of course is u. So very similar to what we have in, well, A just represents vector addition, number 1. Okay? B represents adding a vector to exactly its opposite. Okay? If you did a minus in front of u, it would become v. In other words, distribute minus 1, scalar minus 1, multiplied by that would be that. So those are exactly the opposite vectors. Same magnitude, identical magnitudes, but opposite directions. You add a vector to its opposite, you're going to get the 0 vector. And C represents you add any vector to the 0 vector, and you get the original vector. In other words, the 0 vector didn't change the x coordinate or the y coordinate at all, so you still got the same vector you had. Very similar to the property of addition in real number system, that if you add a number to its opposite, you get 0, the number 0, and you add a number to 0, and you get the same number. Same thing holds in vector addition. Okay? And we got the same thing they did. Good for them. Now, they also show graphical addition and subtraction. Do you need to see that? Okay. Look in the book. It's there. The second basic vector operation besides vector addition is scalar multiplication. Okay? Now, just did one, so it's a bit strange. To multiply a vector v by a scalar c, vector v by scalar c, you multiply each component of v by c. So this would be c times v1, v2, if you're in 2 space. If you're in space, you just put enough out there. And this would be the vector cv1 plus, as opposed to cvs, comma, cv2. Okay, you don't add, there's a comma there. Okay? And that's basically the definition for scalar multiplication of the vector. Now, why do we call it scalar? Because what you're doing, if the c is, say, greater than 1, magnitude greater than 1 anyway, you've just scaled the vector v up by that amount. If c happened to have been less than 1, say between 0 and 1, you scaled it back. You keep the direction, you just change the length of the scale of it. If c happens to be negative, then you change the direction and then scaled also, depending on how big the absolute value of c is, scaling up in the negative direction, or if it's between absolute value between 0 and 1, then you scale down by that amount. And if it's opposite sign, in the opposite direction. And the 2 figures in the text, they show this. Just if that was the vector v, okay, and c is a larger number, then this could be cv, okay. If c was a negative number, then this would be cv, okay. If c was a smaller number, but positive, then that could be cv, okay, depending on the size of c and the sign of c. Now, What if C were -1? What does that do for you? If this is the vector V, C of -1, then CV would be exactly the same magnitude of the vector, just in the opposite direction. So, just like before, I probably didn't quite get that even, but you know, get the point. Just like 3, -2 and -3, 2. 3, -2 would have been 3 units over here and 2 down, and -3, 2 would be -3 in this direction and 2 up. Those would have been exactly that would have been U from up here, and this would have been, if I could draw straight, V from up here. And if you were to add those two together, put the tip of V on the tail of, or reverse that, tail of V on the tip of U, or vice versa, you get to the 0 vector 0, 0. Okay. Now, also that vector -V is called the negative of V, okay? Pretty clever title. So then when you're doing the difference of U and V, just like we do for signed numbers, U minus V, if those were in signed numbers, make up a number. 1 minus, make up another signed number. How about -2? Okay. Then if you do that, you add the opposite of the second number, which would be 2, and that would give you 3. Same thing with adding vectors. U plus V, U minus V, subtracting vectors, would be U plus the opposite of V. Okay? And sure enough, that's how we subtract vectors. You just add the opposite. Okay? Yeah. Okay. All right. Let's erase all ink and go to example 3. Yes. Let's let V, vector V, one of our favorite names for it, equal to vector -2, 5, and U, vector U, be the vector 3, 4. Okay, find each of the following vectors. A is looking for 1/2 V. And that would be what? 5/2 or 2.5 or 2.5, wherever you want to stop. What would be B, U minus V vectors? You can take as many steps as you would like.
That would be 5,
-1. -1. Okay, I think he did the steps in his head. Starting with U, minus, start with the first component, 3, minus a -2, which is 3 plus 2 is 5. Second component, start with U, 4, minus 5 is -1. Minus a positive 5, which would be -1. All right. I've lost where I am. There we go. C is 1/2 V plus U.
That would be 2 and 3/2.
Say that again.
3/2. 2 3/2.
Oh, the first number is 2. Okay, I got what you're saying. 2, comma, and then you would have 5/2 plus plus 8 halves would be 13 halves. Okay, yeah, plus. All right, and they get -1 5 halves, 5 -1, and 2 13 halves. Very good. And they do a figure over there and show some of those things. Do you need to see that? Okay. You're scaling and you're adding. Subtracting, which is adding the negative. All right, then let's look at some other properties of vector addition and scalar multiplication. There's 10 of them, 5 for addition, 5 for multiplication, and these share pretty much the names that we're used to with similar things with integers, similar things with rational numbers, similar things with real numbers. You know, they're all pretty much, not all of them apply to every system, but they all apply here. So here's what we got. U, V, and W vectors in the plane, so keep them two-dimensional, and C and D are scalars. But you could scale them up. I mean, you could use three-dimensional vectors or n-dimensional vectors. It's just a lot easier dealing with one. So let's get these. I'm probably not going to write them all out in gory detail, but I will abbreviate. Okay, the first, okay, here's what you're given. U, V, W are vectors in R2, two-space, two-dimensional vectors. Okay, C and D are scalars. Just numbers. Real numbers, but just real numbers. Okay? First property. Okay? If U and V are both vectors in R2, then U plus V is a vector in R2, in the plane. Now, what we call that property is that vector addition is closed under addition. In other words, if you have two vectors in a plane, add them together, the resultant vector is going to be in the same plane as those two vectors. Okay? Or space, or whatever dimension you're living in. Okay, number 2. Another pretty common one, and this is one we illustrated earlier. U plus V is the same as V plus U. We saw this in two-space when we were adding those two vectors in the plane. The title for this is commutative property of addition. Okay? It's true in real numbers, is true in vector addition as well. Number 3. If you're adding 3 vectors, U plus V, and then add W to that sum, you get the same thing as if you would have added U to the sum of V plus W. Okay? And that's the associative property of addition of vectors. Okay? And this one we saw illustrated earlier, number 4, is that U plus the 0 vector, you only add vectors to vectors, this produces U. And that's the additive identity property. Okay? 5. Man, I'm getting hard to breathe. U plus a negative U, opposite of U, that equals the 0 vector. And basically what that's saying is this is called the additive inverse. Okay. They call it additive inverse property. I usually don't say property after that. It's just illustrating additive inverse, but that is property. Okay. Those are our 5 properties of vector addition. Basically, just what you would expect in real numbers. Same titles, same everything. Okay. Now, there's a part of me that wants to take 4 and say, what if you subtracted a u from both sides and added a 0 to both sides, you'd get number 5. And indeed you would. All right, number 6. We said that addition of 2 vectors in a plane will result in a vector in that plane. That's the closure under addition. Now we say if you multiply C by U, if U is in the space, in an element in the plane, then CU is also in plane. Okay, and this is closure under scalar multiplication. All right, number 7. These go down almost pair by pair by pair. Oh no, actually it does the distributive property next. I say C and write A. Okay. Sorry. My head is filling up again. I don't know why. Hard to breathe. All right. Number 7 is a distributive property. Okay. There's several of these. Here's the first. Well. Okay. C times the sum of U plus V is, what would that be? CU, I see U, plus CV. All right, and this is distributive property, and that's all they call it, I think. I like to add a few words to it. Specifically, it's the distributive property of scalar multiplication over vector addition. Okay, technically that would be the better way to say it, because the next is going to be a distributive property as well. And that next one, is C plus D times vector U, is what? Right. Okay. It's also a distributive property, but that one is distributive property of vector multiplication over scalar addition. So it's sort of the reverse. Stuff number 7 is scalar multiplication over vector addition, and 8 is scalar multiplication over scalar addition. Okay, sorry.
When you say vector multiplication over scalar addition, makes me think some vector gravy you're just pouring over.
Right. You're thinking food. You're hungry, I can tell. All right. All right. The next one, the next one is a form of associative property of multiplication, but we've got some problems with that. So we're limited to just a few. Here's the one. C times du is the same as CD times u. okay? And they put the CD in parentheses. That is an associative property.
But it's not commutative,
No. Yeah, notice we did leave out commutative property. Actually, for scalar multiplication, it wouldn't really matter if
right?
you
It could
put
be CD or
vector
C.
u times c is still the same as c times u. So they left that one out, I think, completely. But we usually write the scalar in front. That's the only reason. Okay. The associative property here, we can do scalar multiplication. Okay. And this associative property of it's multiplication, but it's scalar multiplication with vector multiplication, because we haven't defined what multiplying two vectors is yet. We know what multiplying a scalar times a vector is. That gives you a vector. And then multiply that vector by another scalar, which that's scalar multiplication. So we know what that is. That's the same as multiplying the two scalars first by the vector. So it's that form of associative property of multiplication. We can't do much more, in fact, I would say at all, because you can't do a C times UV because we haven't defined what vector multiplication is, UV. Okay. Now, the last one, pretty simple. 1 times the vector U is the vector U. Okay? And that's the multiplicative identity element. Okay? Just like this one is the additive identity property. This is multiplicative identity property. All right. Now they do some proofs here, and they do them in two-dimensional. That's why they did two. It makes it a lot easier. You just do component by component, and say I think the one they did was number 3. You do U1 plus U1 U2 plus V1 V2 plus W1 W2. Add these two together, and then add that one. You get U1 plus V1 plus W1. How would you do it that way? You get V1 plus W1, V2 plus W2, add it to U1 plus U1 U2, and you get the same thing on both sides. It's just writing them out. Yeah.
We just did cross products and all that in Cal 3, and I was like, I haven't gone over multiplication.
Yeah.
And I was like, oh wait.
The proofs of the other 8 properties are left as an exercise 57, which you will be free to do if you choose. Okay. It'll be one that we will mention. Okay, now that was mostly staying in 2 space. Let's move up to n space. In other words, vectors in Rn. That's not a registered nurse, by the way. Okay. The discussion of vectors in the plane can be expanded to the discussion of vectors in n space. I would first take it to 3 space and then in any n space. An ordered n-tuple is what they call these. That's you have ordered pair, ordered triples, ordered quadruples, quintuples, and stuff, so they call them n-tuples. Okay. Vector in n space would be x1, x2, x3, x4, up to xn. Okay. Now, 2 things about it. The n-tuple tells you how many elements you have. I use the term elements, technically components you have. That's what the n stands for. The other word there, though, is ordered n-tuple. The order does matter. You can't flip-flop or switch around or jumble the components. That makes totally different vectors. Okay? So the order matters, and you have to have the number. Now, what's that?
Can't
Right. Yeah, we'll deal with that. But right now, they're all either column vectors, remember, are either columns or scalars, so there's nothing to switch. I mean, columns are rows, so there's nothing to really switch there. But the deal here, and this goes back to also to what we're doing in matrices, is you can't add a vector in 3 space to one on the plane unless you add a third dimension to the one on the plane. So you have to have the n.
If it was on the Xbox plane, the z would just be 0.
The z would be 0. But the way we lined it up, that was x, that was y, that was z. That would be the yz plane, and x would be 0. But you can't add a 3 tuple to a 7 tuple. You just don't have enough things to do it, and it doesn't make sense anyway. So we stay in the space. That's why the n matters. The number of elements or components matter, and also the order matters. Now, so when we're talking about this, what is R1? Second? It's a number line, yes, the real number line. So you're talking about real number system, okay? And then R2 would be some plane, okay? Any two-dimensional plane. Yeah, with 2 axes, exactly, okay? R3 would then be space as we understand it. Yeah, we can't picture any other than 3 space, okay? And R4, something beyond my visualization.
That would be 3 space, but with time.
Okay, I can tell you've read some. Okay, you can think of it that way.
Because, that would just kind of be like an active.
A what?
Graph. That would just be like an active graph that's changing.
That's moving all the time.
Yeah.
Perhaps. How about R5 then? We're beginning to lose it. If you didn't lose it in R4, you lost it in R5. But still, that would be a space made up of quintuples, vectors. And whatever that is, that would be it. Okay.
3 would take care of space, 4 would be time, possibly.
Space-time continuum, yeah. Einstein would call it.
5
yeah, it gets totally wacky.
Something we
right.
Really got
right.
definition for.
But still, we could talk about them and use them. A vector in 5 space or any n-tuple space greater than 4, or wherever you want to do it, would just be, say, U1, comma, U2, comma, U3, comma, U4, if I could write, comma, U5. That's a vector just as good as any old vector would be.
What
we just
application does that have?
I have no clue. But
I guess
theoretical linear algebra. Okay, right. An n-tuple can be viewed as a point in Rn, which you can't even visualize, so why would you view it that way, with the xi's as its coordinate, or the vector who's coming from whatever the origin of that n space is out that many places. So this, I did u, they did x. This would be the vector u in 5 space. Okay, they did n space. Okay. Now, within any space, pick your space, then, okay, whole number of spaces, okay.
I mean, if we can do 6 space, 13 and a half seems just as far.
Yeah. It really does, doesn't it? Okay. With any 2 vectors within any n space, they're equal if and only if every one of the components are identical. Okay. So if this was u and you had an x in 5 space, that would be x1, x2, x3. Those 2 vectors, u and x, would be equal if and only if U1 is equal to x1, U2 is equal to x2, U3 is equal to x3. Every one of the components are identical. Now, identical maybe not looking. If U4 was 3 and X4 was 12/4, yeah, they're still the same value. Okay, they don't look the same, but they both have the same value. Okay. If and only if the corresponding components have the same value, exactly the same value. Okay, the sum of two vectors, and again, you can only add in a space. So if you're adding this U to the X in 5 space, that's doable. Okay, I can't picture it, but it's doable. Okay, but you can't add U to a V that's in 4 space because you'll have a U out there that doesn't have a V to add to it.
But you couldn't put in a V that was 0, right?
You couldn't guarantee that would be the same.
In 5 space.
Right.
In 2 and 3 space, probably could. Because if it was on the XY plane, you could add a 0 for Z.
Okay. Okay, but let's say it's not the XY plane. Let's say it's a plane like this, or up like this, and then you can't say you can't add it to a vector in free space because this already has an X component, a Y component, and a Z component, but it's in a plane, so you still, you don't have anything you can set to 0 and be fair about it. Okay, so you only add within a space. Okay. Now, the sum of two vectors in Rn, the scalar multiple of two vectors in Rn, are called the standard operations in Rn. Okay, and they're defined very, very similarly to what we did just a few minutes ago when we were talking in 2 space. So let's let U be a vector in space. U1, U2, U3, comma, dot, 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 all the way up to comma, UN, however big n is. And V also is a vector in that n space, V1, V2, V3, dot, 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 up to V sub n. Same n, okay? Now, these are two vectors in Rn. These are both in Rn. And C is a real number. Okay? These vectors are in Rn. Then the sum of UV, U and V, is defined to be just like we defined it before. U1 plus V1, comma, U2 plus V2, comma, U3 plus V3, comma, dot, 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 comma, all the way up to U sub n plus V sub n. Okay? That's how we add the vectors. That's our standard rule for it. That's definition of vector addition. Standard. I keep saying that because later they're going to do some weird things. Okay. Scalar multiplication in space of U by some vector, some scalar C. So CU would be CU1, comma, CU2, comma, CU3, comma, dot, 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 all the way up to comma, CUN. Just like we defined before. Okay? Now, also similar to what we did before, we can introduce all the other things. The negative of U would be negative U1, comma, negative U2, comma, negative U3, comma, dot, 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 comma, all the way up to negative U sub n. You just negate every component in U. In other words, your C is a minus 1. And that's what you've just done. Okay? When then you talk about vector subtraction, U minus V, it's just U plus the opposite of V, the negative of V, which we just defined in the one above. And that gives us, if you actually did that, it would be U1 minus V1, comma, U2 minus V2, comma, U3 minus V3, comma, dot, 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 comma, up to U sub n minus V sub n. Okay. Now, in the Rn space, Rn, you also have a zero vector. The difference here is this zero vector would be 0, 0, 0, dot, 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 until you get to the nth 0. You have to have n components of 0, okay, for the zero vector. It would be 0, 0, 0, 0, 0, like we're used to. It would be 0, 0, 0. You have to have n of them. Okay. So let's do example 4. You see, with these definitions, it really doesn't matter how many dimensions you have. You're not really drawing them. You're just doing the things. Yes, exactly. That's why I even have to have good luck drawing 3 space on 2. So getting above that, the luck just...
Computer software, but
after that, hang it up, Jack. Yeah. Here we're in good old 3 space. U is the vector minus 1, 0, 1. Vector V is, also, to do anything here, you better be in 3 space, 2, negative 1, 5. And they're both in R3, so these are in R3, obviously. They got 3 components. Find each of the following vectors. A is U plus V. What would that be? 1, negative 1, 6. Done. B, 2U. Happy birthday. That would be?
Negative 2, 0, 2.
Got it. Okay. C, V minus 2U. Got it. Okay. 4, negative 1, 3, negative 2, 0, 2, and 1, negative 1, 6. Perfect. All right.
More arrows.
Yes.
I
And
think that's the same thing we just went
it is identical to it. The one before was, I think, 2 space, wasn't it?
Yeah, it's in 3 space. We did that.
No, it's vectors in a plane, and this is Rn, so this is vector in space, okay? And everything is identical, the name and everything. By the way, they have a pretty picture of William Rowan Hamilton here, considered to be Ireland's most famous mathematician. And I'm not absolutely certain about it, but I'm almost certain this is true. And it may be a different. But in quantum mechanics, they have an operator they call a Hamiltonian. And I've always assumed it's the same Hamilton, which is very interesting because he died 35 years before anything in quantum mechanics, at least 35 years before anything in quantum mechanics had been conceived. But my guess is he came up with a mathematical construct that later the quantum mechanics, the physicists who did that said, hey, this thing works really well here. And they used it there. I don't know that for a fact, but he's the only Hamilton I know of, so they call it the Hamiltonian. I bet you it's his. So he was a pretty clever guy. He had no clue of some of the applications that some of his work was going to be applied to, which is really a statement about how broad his thinking was. And these are those 10 here, identical to the 10 we saw before, same names and everything. Before it was 2 space, this was n space. What's that?
Not going to run again.
Right. And then we'll go to example 5. And we're doing okay on time?
About
20 minutes, excellent. Making great progress, I think, today. Okay. See, what I'm seeing is I see all these arrows in my book where I started, but I've taught from this book several times, so these weren't all the same terms. So, all right, let's start with U. And again, now we're in 4 space. Okay, 2, -1, 5, 0. Okay, V is 4, 3, 1, -1. W is -6, 2, 0, 3. There are vectors in R3, R4. Okay. And they don't have any scalars. I thought they were going to do. Find X using each equation. So we're looking for X. Okay. Guess what? X is going to be in 4 space too. Okay. So let's do A. X is equal to 2U minus V plus 3W. 2U minus V plus 2W, 3W. I have a good memory. It's just real short. Okay. All right. That first one's a U. The last one's a W. Sometimes they look sort of similar, but they're not. Okay. Now, you want to try to do this all in one fell swoop, or you want to?
Well, 2U would be 4, -2, 10, 0.
Okay. V plus 3W. Let's just do that.
3W is -18, 6, 0, 9. So V plus that would be -14, 9, 1, 8.
8, you said. Okay.
And then
Yeah.
subtract those.
Yep.
Add and flip the signs. That gives 18, -11, 9,
Let's see how they did. 18, -11, 9, -8. Good for them. Let's try to do B. Yuck. I'm real tempted to erase. I think I will. Huh? Sorry.
we're finding X on this one too. Very interesting.
Yeah.
And we're not reusing X, right? No.
Okay. B is you're finding X when 3 times X plus W is equal to 2u minus v plus x. Okay, now, how would you suggest we proceed with this one? Yeah. Okay. We need to solve for x, so we need to simplify both sides, do whatever it is. So that would be 3x plus 3w is equal to 2u minus v plus x. Now what? Second? You could do that, or well, let's go and subtract the x from both sides. Okay, that would give, and while we're at it, subtract 3w from both sides. And that will give you 2x is equal to 2u minus v minus 3w. And then divide by 2. Okay? I think this would be just about as simple as any other way. Because rather than write all the numbers down, let's let algebra do as much work as you can. So now this x vector would be u, which is 2 minus 1, 5, 0, minus v over 2 would be 2, 3 halves, 1 half, negative 1 half, right? Minus 3 halves w, u, that would be, now I did get, okay. Oh, you're doing from the first? Yeah.
Because I wrote down what 3 to
Yeah, you wrote that earlier, right. And just having that. So that would be a negative 9, 3, 0, 9 halves. Okay.
Now we just subtract everything?
Yep. Subtract twice, actually. It's minus 5 halves. Minus. I may have done it wrong, but let's see. Yeah. Okay. Get the same?
Almost. On the last one. Oh, 9 I think so.
Okay. Now, how did they do it differently? This is possibly a little bit better, probably was. They did 2u minus v minus 3w. Calculated that one and then took half of that. So you didn't have as many fractions as long. Okay. You didn't have them until the very last step. What?
They have that the original x we found is actually double the second x.
Oh, really?
Yeah, if you see where it says x equals 1/2 and then that vector.
Oh, well.
That's the same as the first one.
Yeah, well, okay, I'm sorry. Yeah, you're right. And that's probably why they did it the way they did. Because they said, you've already calculated that. So I just didn't, I had erased mine, so I didn't have it there to look at it.
Oh,
yeah.
No, it's just, got a little extra.
Clever, though, yeah. All right, the zero vector in Rn is also called the additive identity element, or additive identity property, or whatever.
Anything it's itself, multiplied by anything it's it.
Yeah, okay. Similarly, the vector negative v is called the additive inverse of v, just like we did before. And by the way, 1 is the multiplicative in identity element in Rn, and we'll stop there. We won't do a multiplicative inverse because that hasn't been defined yet. The following theorem summarizes several important properties of the additive identity and additive inverse in Rn. We haven't quite done these exactly, but it seems like we've done them. We've talked about them anyway. So let's let V be an element in Rn. C is scalar. Okay. Then these properties are true. Additive identity is unique. There's only one of them, and that would be 0, 0, 0, 0, dot, 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 comma, 0, as long as you had n zeros, okay? Now, the other ramification of that would be if v plus u is equal to v, then you know this u has to be the zero vector. It has to be. There's no other way you can add. There's no other vector you can add to v to get v except the zero vector. Okay?
Unless v is a zero vector.
What's that?
U is v.
Yeah, and that would be a zero vector. Okay? All right. Yes.
And everything's zero. But that's
Yes. The additive inverse of v is also unique. Additive inverse also unique, meaning, let's say you had v minus v1 minus v2 minus v3 dot 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 minus vn. That's the only additive inverse you have for v. Okay? The other ramification for that is that v plus u equals 0. If that's true, then v has to be minus u, and vice versa. U would have to be minus v. Okay. They said that u is equal to minus v. All right. The third such property is if you multiply the scalar 0 times the vector v, you get the zero vector. If v is an n space, then the zero vector is an n space. If you multiply a scalar times a vector, you get a vector, but you scale every unit in that vector, v1 times 0, v2 times 0, 3, and you get 0, 0, 0, 0 in option. So you would have that. Okay? 4, going the other way, multiply any scalar, not necessarily 0, by the zero vector, and you get the zero vector, because c times 0, c times 0, c times 0, c times 0, c times 0 is all zeros. Okay? And number 5. If CV is equal to the zero vector, then one of the previous has to be true. Either C is equal to 0, the scalar C is 0, or the vector V is the 0 vector. One or the other, there's no other way to get that. You don't have any combination of them that's not going to be, there are no combinations. That's it. And then finally 6, and this is hope pretty obvious, the opposite of V is equal to V. If you negate all the elements in V, all n of them, and then negate them again, you come back to V, what V was to begin with. And they prove that first one, additive property being unique, and they do it without assuming any values V1, V2, V3. They just do it using other properties we had. And their clever little thing is to add the negative V to that, and you get they take a long time in getting there, several extra steps, but they do show that U would have to be 0. Okay. Now, vectors have a wide variety of application in engineering and the physical sciences. For instance, to determine the amount of force required to pull an object up a ramp so that that has an angle of elevation theta, using the figure that's over here. And the picture that's on the other side, sorry. You basically set up your vectors just like you did in physics. The weight vector is always toward the center of the earth, and then break that into components parallel to the ramp and perpendicular to the ramp. And what you're having to pull is the parallel component, because the perpendicular component is balanced by the normal force of the ramp. So hopefully it's stuff that you have seen and done before.
Yes.
Okay. Now, we got time for linear combination vectors?
We got about
5 minutes. I think maybe we can. This is just and it's a concept we're going to use over and over and over, so it's important that we have it. An important type of problem in linear algebra involves writing one vector as a vector x as a sum of scalar multiples of some other vectors, v1, v2, up to vn. That is for scalars c1, c2, up to cn. So you write it this way: vector x is equal to c1, v1 plus c2, v2 plus c3, v3 plus dot 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 plus c sub n, v sub n. Okay. If you can do that, and generally you can, if you have, well, I don't want to get too far back. If you can do that, if there's a set of v1 through vn, such that you can write any old vector x as a linear combination of those, then that will be applying meaning to that later, okay? And this is what we mean by writing x as a linear combination of other vectors v, okay? It doesn't have to be x and v. You can mix and match and do whatever. But that vector x is called a linear combination of the vectors v1 through vn. Now there's a little discovery over here on the left, and example 6 on the right. You want to try to do one or the other, or both of them. We don't have lots of time. We can do one now and one later. next time.
Go ahead and do example 6.
That's what I was going to say. I think that might be a little more useful. So let's say vector x is equal to -1, 2, -2. Oh, we're in 3 space. Vector u, yeah, 0, 1, 4. Vector v, -1, 1, 2. And vector w, 3, 1, 2. Okay. They're all in R3. Find the scalars a, b, and c such that this is true. X, vector x equal a times v plus b times u plus c times w. Did I get it wrong?
You got your u and your v mixed up.
Oh, okay. We'll have u here. Yuck. Yeah, okay. We did u first and v second, and then w.
Plug in our vectors first.
That's it, exactly. -1, 2, -2 is equal to.
Do we want to distribute the a, or you want to just write it out first?
Do you have a preference?
And we can go ahead and distribute
Okay.
it out if you think that's a good idea.
Like this?
That works. We can just write it.
What were you thinking?
We can just keep doing this.
What's that?
We can just keep doing this.
Okay.
Trying to do too much at once, I think.
Okay. Now, what I would suggest is doing a matrix.
Ah, yeah. I like that.
Okay. See what
Yeah,
we're.
I see what you're doing. You're just going in an odd order. I was reading it left to right. You were doing from right to left.
Yeah, well,
Sort of.
what I'm going to do is put my variables here and the constants here. So the first one would be 0a minus 1b plus 3c is equal to -1. So these are my coefficients. Okay. And the last one being okay. These stand for your A, your B, and your C, and these are your, that's called X1, X2, and X3. They could be any 1, 2, 3, but I just chose that.
So, row echelon form?
Yeah.
Okay, switch row 1 and 2.
All right. Okay. You think I can also?
Negate
Oh.
the second row.
No. What I was thinking, that third row. Yeah.
You can also negate the row if you want.
Okay. Yeah, why not? I was trying to see if there's something I wanted to do with it first, but yeah, might as well. Okay. What's that?
-5.
Got it. And then
Add row 2 to row 3 and subtract it from row 1.
yeah, I'm running out of room, so I think I will go up here.
Actually, we can go ahead and negate the bottom row. Well, no,
Well, I want to add first and then negate.
yeah, and see what happens.
Okay. Okay, this is going to be a little crowded at the top, but hopefully not too bad. 1, 1, 1, 2, 0, 1, -3, 1, and 0, 0, -4, -4.
So do a -1/4 in the bottom row?
Yeah. Okay. Now the question is, do you want to reduce row echelon form or back substitute?
We can just do it this way.
What's that?
Oh, either way.
Which would you prefer?
I can do both. I can do this one and just plug in from here.
Okay, which you
Back
prefer?
substitute.
Back substitute. Be fine. So this says that C is equal to 1. Okay. B minus 3 is equal to 1. So B is equal to 4. And A plus 4 plus 1 is equal to 2. So A is equal to -3. Okay. Let's see if we found A. Whoa, 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 whoa. I must have messed it up really badly. They got C being a -1. Okay, let's look at our equation, make sure we got that right. -1, 0, -1, 3, -1, 1, 1, 1, -2. Did I write the problem down? I did write the problem down wrong. That makes all the difference in the world.
Oh my gosh.
I know.
Well,
But,
we are over by like 5 minutes.
yeah, but in reality, we never used that until the very end. Did we?
Let's see.
Yes, well,
Yeah, it changed. Let's see. Because that would have been negative here. And, negated row 2. Switched it.
oh yes, we did. At the very first step, we did -2 row 1 plus row 3. So that would have made that a 4, that would have made that a 3. Right there. See in that step? Okay. Then when you added,
Wouldn't that be a -3?
let me see, -2 times -2.
Oh, wait. Excuse me. You're right.
Okay.
I didn't see it was a -2.
And then when you add those two together, that gives you 0, -4, +4. Okay? And that would make this a -1 right there. So C equal -1. And then the rest of them, I think, fall through from there.
Just flip the sign.
B is equal to, no, B minus, no, B plus 3 now. Yeah. plus 3 is equal to 1.
B is negative
So
2.
B is equal to negative 2. Okay. All right, B is equal to negative 2. And then A is A minus 2 minus 1 is equal to 2. So that'd be, looks like 5, doesn't it? They get A equal 1. Ah! C is equal to minus 2. We got, in that minus 1, we got that right. I can't find it now. B is minus 2. So how do we, did I change that? So A minus 2 minus 1 is equal to 2. Which? Oh, that's the one I didn't change. I didn't change this one and this one. I thought I had. That'll be a minus 2. So those go out and it'll be a 1. No, 1, isn't it?
Yes, it's negative 1. Plus 2 plus 1 is 1. Yes, 1.
Yeah, 1. Right. Okay. Okay. All right. Yes, that's what they got.
Okay. We are only 10 minutes over.
Okay. No extra charge, so, okay? Homework exercises, you can do 1. You can do either 3 or 5. Either 7 or 9. Any of the odds 11 through 15. Do 17. Any of the odds 19 to 23. Either 25 or 27. Do 29, 31, either 33 or 35. Do 37. Any of the odds 39 to 43. Either 45 or 47. Try 49. 51. Oh, 51 is true false. You can do it if you want to.
It's true. It might be false.
53 would be fine. 55, I think, would be a good one. And then you choose if you want to do any of the rest of them. Okay, good deal. We'll pick up with 4.2 next time. Was it? What did you say? I missed it.
So don't forget to stop.
Right. Okay. Finally, after an hour and